so we will be doing H2 regions. So what are H2 regions? So H2 refers to hydrogen with one electron removed from it. So it's basically proton, right? So if you have a massive star which produces a lot of photons and a lot of high energy photons, right? More massive a star, higher its black body or effective temperature is, the more UV type photons it produces. So what are H2 regions? So if you have a sort of a star, say O or a B star, right, which has a temperature which is like more than 30,000 Kelvin or something like that, it produces a lot of photons with H nu greater than 13.6 eV. Right? If you have photons with energy greater than the ionization potential of hydrogen, it can ionize neutral hydrogen. And these O and B stars have significant non-negligible fraction of photons which are ionizing photons. So these photons are called hydrogen ionizing photons or Lyman continuum photons. So it's sort of obvious because the Lyman continuum corresponds to n equal to 1 to n equal to infinity. Basically, n equal to 1 bound electron is removed and sent to n equal to infinity level, which is nothing but the continuum. Okay. So that is 13. So that's why these are Lyman continuum photons. Okay. So right. So what happens is if you have a neutral ambient medium and you put this star in such a medium, what it will turn out is that it will create if the ambient medium is sort of a perfectly uniform medium, it will create a spherical ionized bubble. So ionized bubble. And the outside medium will still be neutral. And this is constant density. So we are only considering, for simplicity, let's only consider only hydrogen. We are ignoring helium and metals and everything else for now. Okay, so you have a neutral hydrogen ambient medium, you put a ionizing star in it. What the star does is it produces a lot of photons with energy greater than 13.6 eV, and it ionizes some region around it. Okay, and this spherical region is called an H2 region or a Stromgren sphere. So this is a size RS0. This is an ionized bubble, and this is called Stromgren sphere, after the person who figured this out, Stromgren. Okay. So a quantity of interest is Q naught, which is nothing but number of Lyman continuum photons emitted by the massive star per unit time. Right? Basically, we are not interested in the total luminosity. We are only interested in the luminosity in photons which can ionize the neutral hydrogen around it. Okay, and that's just equal to nu naught to infinity L nu by H nu d nu. Okay, this is easy, right? L nu is the luminosity of the star, per unit frequency. So L nu d nu is energy in photons coming out from the star per unit time from frequency nu to nu plus d nu. And if you divide by H nu, this becomes the number of photons ionizing photons coming out of the star per unit time. Okay, so this is Q naught. And for B stars and so on, we will actually be normalizing this to about 10 to the 49 photons per second. 10 to the 49 ionizing photons emitted by these OB stars with some temperature per second. So we'll actually be normalizing things to this. As you go to lower and lower mass stars, right, you have this Planck spectrum. You can approximate stars as black bodies. And at high frequencies, the intensity is exponentially smaller. So if you go to lower temperature stars, the ionizing photons become exponentially rarer. So you can have thousands of sun-like stars. They don't really do anything. Even if they have 1,000 times solar luminosity, each photon has not a lot of photons have energy greater than 13.6 eV. Okay, that's why it's only O stars and sometimes also B stars which are most important for this. Okay, so let NH be the neutral hydrogen number density in this ambient medium. Number density. So in steady state, right, what happens is, so you have this ambient medium, you put a star, it will start ionizing a region around it, but it will reach a steady state. And the steady state is between ionization due to these photons and recombination of electrons and protons, which sort of is the reverse process of ionization. So basically, you have hydrogen plus H nu giving rise to proton plus electron, or let me just call it H plus. Right. So this is photoionization. The inverse of this is, the PI is photoionization. Inverse of this is radiative recombination. Okay. So in H2 regions, roughly there is a balance between photoionization and recombination. This is not true for in general. You can have a situation where you have ionization due to collisions. You can have collisional ionization and radiative recombination. They're not like exactly a reverse of each other, but you can also have that. Like collisions can excite the higher states, and the higher states, or collisions can ionize an atom, and they recombine and produce photons. That can also happen. But in these conditions, when you have so much Lyman continuum photons, this balance can work out. Okay. So in steady state, what happens is number of total number of ionizations. What is that? Is equal to ionizations per unit time is equal to Q naught. So whatever Lyman continuum photon that's produced by the star, all of it is ionizing some neutral hydrogen. Okay. And in equilibrium, the total number of ionizations per unit time is equal to total number. So in equilibrium or in steady state, Q naught is equal to the total number of recombinations per unit time. So what is recombination? So n electron, n proton times alpha recombination times. So this NE NP times alpha is the recombination rate per unit volume. So you have to multiply this by volume, which is 4 pi by 3 r S naught cube, right? So this is the total number of ionizations. Every Lyman continuum photon is ionizing something. And This is the total number of recombinations. So this will give you what RS naught is, right? This gives you the size of your Stromgren sphere. So what do we get? We get, if you just do this math, you get RS naught is equal to 3Q naught by 4 pi NH squared alpha B. Let me write this alpha recombination as alpha B, and I'll come to what it means in a bit. So this is the size of your sphere, RS naught. So what have I done? So I have made actually several assumptions here, which you may not have paid attention to. I have assumed that assumptions. What are the various assumptions? So first, I have assumed that once this bubble is ionized, its number density does not change. This star has turned on, it has ionized this bubble, but its number density of the electrons and number density of protons is the same as the initial neutral hydrogen number density, right? So this is Ne equals Np equals Nh. Right? So the initial number density and the ionized number density are equal. But that cannot be true for a long time scale, right? If the ambient medium is at 100 Kelvin, and if you ionize it at 10 to the 4 Kelvin, you're already overpressured. And the other factor of 2 also comes because you have increased the number of atoms. You have made 2 particles from 1. So the pressure has to increase. And what this increased pressure will do is it will drive a shock in the medium. But we'll actually come to it that happens on a time scale which is much longer than the time scale that we are interested in. So this is the first assumption. Got it? So inside this, you have electrons and protons. Outside, you have neutral hydrogen only. Right. So what is the second assumption? The second assumption is the time scale to form this Stromgren sphere is much less than the lifetime of the O star. I mean, that's also obvious. If the O star dies before this steady Stromgren sphere can form, this calculation has no meaning. So time scale of formation of Stromgren sphere is shorter than the time scale of O star lifetime. What is the third assumption? Third assumption is that Stromgren sphere has a sharp edge. What I said is inside everything is ionized, outside everything is neutral. It has a sharp edge. Otherwise, you'll have the ionization fraction is high inside, it will have like a slow transition, it becomes 1. This is the third assumption. And what is the fourth and perhaps the most important assumption? The fourth assumption is radiation produced due to recombination. Right? So let's see. There is radiation produced due to star, right? But you'll have ionizations, you'll have protons and electrons there, but they will also recombine. And as you can see in this reaction, in the reverse reaction, recombination produces photons. There is also photons produced due to recombination. But in this argument that I made, I've ignored all of that, right? So radiation due to recombination can be ignored. This is the fourth assumption. And this assumption is actually true only in a certain limit and only in a certain way. Okay. So if you have you have hydrogen, so you have n equal to 1, n equal to 2, 3, and so on. Okay, and there are L equal to 0 and 1. There is L equal to 0, so there is 1s state here, right? There is 2s, 2p state here, and so on. So Imagine that you have a transition from, say, n equal to 3 to n equal to 1 state. Okay. You have this recombination. This will produce no, not this recombination. You have this transition. Okay, n equal to, so recombination means that it has to start in an ionized state and then come to some state. What I'm saying is once you are ionized and when you recombine, you can recombine any of these states. You can recombine in 1s, 2s, 2p, and so on, depending on the probabilities of these things happening. Now, if say some electron recombines in this state, it can actually quickly transition from n equal to 3 to n equal to 1 through this line emission. This is Lyman beta. This is Lyman beta transition. And Einstein A values the strength of these transitions very high. And once you create this, so once this transition happens, it will lead to a photon, and this photon will leave here and it will be immediately absorbed here because there is all neutral hydrogen sitting around it. As soon as this Lyman beta photon touches any neutral, most of the neutral hydrogen is in the ground state, right? So as soon as this Lyman beta photon hits an atom, it will again re-excite it from n equal to 1 to n equal to 3. So it's as if uh, this emission never quite happened. All these transitions to n equal to 1 will be reabsorbed by the ambient gas. Makes sense, right? Because most of the neutral hydrogen is in the 1s state. And as soon as any of these Lyman photons are produced, they'll just excite the ambient neutral hydrogen. So this is the case B recombination. This approximation in which the Lyman series transitions, including the Lyman continuum transition, are immediately reabsorbed, is called case B recombination. And this applies when Lyman continuum photon optical depth of Lyman continuum photons, lambda, or so lambda Lyman continuum photon is smaller than the system size. Okay. So this is called case B reionization. So case B reionization, basically you ignore recombinations to the n equal to 1 state, because if those recombinations happen or those transitions happen, they immediately get absorbed because of the excitation of ground state to a higher state. Okay. So this applies in H2 regions, which are dense regions. But the other case is case A recombination. In case A recombination, the Lyman continuum photon has a mean free path which is bigger than the system size. So in that case, if a Lyman continuum, so if you have a recombination from continuum to n equal to 1, that photon can leave the system. It is not reabsorbed. I mean, this case A and case B you will encounter a lot of times, so it's better to understand this conceptually. So in low density media, like in the IgM, intergalactic media, case A is used. In high density media, like H2 regions and interstellar medium, case B is more relevant. Okay. So this is lambda Lyman continuum is greater than the system size. System size can be the size of neutral hydrogen cloud. Right? If the size of the neutral hydrogen cloud is small compared to the mean free path of your Lyman continuum photon, the Lyman continuum photon can just leave. Okay. So that's why we have used in our recombinations, we have used case B recombination uh, recombination rate or recombination rate coefficient, because everything recombining to n equal to 1 is immediately reabsorbed by neutral hydrogen around. Uh, these Einstein A values for a lot of these allowed transitions are actually like 10 to the 4, 10 to the 8, very high. And the lifetime is inverse of Einstein A value. So that means if you have, say, n equal to 3 state, it will very quickly on a time scale of 10 to the minus 4 to 10 to the minus 8 seconds transition to the ground state. So you can assume that all neutral hydrogen is in the ground state, because they just come immediately to the ground state because Einstein A's are very high. The lifetime is very short of these excited state. Okay. Okay. So now if we plug in the numbers for RS naught, this Stromgren sphere RS naught, what we'll get is this is about uh, 9.8 times 10 to the 14. No, not 14. 10 to the 18 centimeter for Q049 to the 1/3. You see, this had a power 1/3. This expression had a power 1/3. What you're doing is recombination rate density times volume equals Q naught. That's what you're doing. So that's why you have this 1/3 power, and the density dependence N2 minus 2/3. And alpha has a temperature dependence. The recombination uh, rate coefficients depend on temperature. And if we put in the temperature dependence, this is how it 0.28. This is how it goes like. Yeah, this is sort of, there are tables and so on, and fits for things like alphas. So alpha is a function of temperature. There are tables like that or some simple power law fits, and this is based on that kind of a approximation. So what does Q049 means? Q049 means Q0 in units of 10 to the 49 Lyman continuum photons per second. If your O star is emitting 10 to the 49 Lyman continuum photons per second, Q049 is 1. Similarly, N2 is the ambient neutral hydrogen density. N2 is basically neutral hydrogen density divided by 100 per centimeter cube. So 2 is 10 to the 2, right? So this is 10 to the 49. So this is Q naught by 10 to the 49 per second. And T4 is nothing but temperature by 10 to the 4 Kelvin. So that if you put in the typical values, you just have to read off the uh, coefficient. This is about 3 parsec, right? 1 parsec is 3 times 10 to the 18 centimeters. So this is about 3 parsec. For typical values, the Stromgren sphere is like few parsec. If you go to a denser region, the Stromgren sphere becomes smaller, because in a denser region, recombination becomes more prevalent. If you have a brighter star, or if you have a lot of stars forming together, then the Stromgren sphere will be bigger because it goes like Q to the 1/3. It's very physically intuitive, all this. Right. So let's see. Let's see if you have understood it. So would you normally get, say, Lyman alpha emission from H2 regions? And it's a question. Do you think you'll get Lyman alpha radiation from H2 regions? Hint, in the case B, we are using case B recombination. Yes, so you won't. I mean, in this idealization, you do not expect uh, Lyman series lines and continuum, but you do expect H alpha because uh, H alpha is 3 to 2 transition. So what you have is you have ionized a photon and you have ionized an atom, and this free electron can go to any of these n levels, np states. And if it sort of recombines into some n state, there will be cascades. It will go from high to low to it will come down, and all these uh, transitions will give rise to line emission. So all line emissions will be seen except for the ones leading to n equal to 1 level, because that photon can be immediately absorbed by the ambient neutral hydrogen medium. So sometimes people define emission measure or EM as, I mean, this is nothing but a strength of uh, emission. So this is NE NP times ds. So if you have, so ds is the line of sight integral. So if you have a, say, an H2 region with some electron density and proton density, NE NP ds integral is the emission measure. And since recombination goes like Ne times Nb times alpha, right? That's the recombination rate per unit volume. So this will be, emission measure will be higher for uh, higher recombination rate. So the surface brightness, if you recall, we had talked about the surface brightness. Emission measure is proportional to surface brightness, right? Because any NPDS does not depend on where you put the source. It's an intrinsic property of the emitter. So this is basically proportional to the surface brightness, which is an intrinsic property of this emitter. And so for a Stromgren sphere, what is the average emission measure? So what would be the average emission measure? That's nothing but so any NP for a simple Stromgren sphere that we are considering with only hydrogen, Ne and NP are equal to NH. Because I said that the density structure is not changed. So this is just so if you have a sphere like this, if you look at the center, the value of any NP ds is nothing but NH squared times this length, which is 2 times the RS0, right? But at the edge, it will become 0 because this line of sight integral goes to 0 at the edge of the Stromgren sphere. So the average emission measure is Ne NP ds times the area divided by. So this is the area averaged emission measure. So this is basically this. So you take the emission measure along this full all these different lines, and you divide by the area. So ds times dA is nothing but dV, right? Line of sight length and the area on the sky. That's just dV. So this is basically volume. And since Ne and NP are NH, which is a constant, it just comes out of the integral. So that's just NH squared 4 pi by 3 RS naught cube divided by, what is the area? Area is just pi times RS naught square. And so this is just 4 by 3. So the area average emission measure is just 4 by 3 NH naught RS naught cube. But RS, sorry, not RS naught cube, RS naught. How do I delete it here? Got it? But we know how RS depends on, NH naught and Q naught. So this is, if we plug in the numbers, the average EM is equal to 4.2 times 10 to the 4 centimeter to the minus 6 parsec. So, notice the units. This is per centimeter cube times centimeter. The centimeter to the minus 5, but we put in centimeter to the minus 6 times parsec so that we get a number which is not like very big. Just like H naught, the Hubble parameter, is basically 1 by time, but we express it in kilometer per second per megaparsec, so that kilometer and megaparsec cancel out each other. In the same way, sometimes this kind of a unit is used. And then we have Q0 dependence, Q0 49 to 1/3, N2 to the 4/3, and T4 to the 0.28. So this is just dependence on the radius. You can see I have just plugged in this expression here. So if you increase your density, your emission measure increases. That's sort of expected. And similarly, if your ionizing photon flux increases, your emission measure increases. Because everything is neutral outside, no? Fully ionized, fully neutral. That's sort of the ideal, simplest model. Line of sight, this is ds. So if you want to calculate emission measure along this line of sight, so you take the density here, electron density here, proton density here, and multiply by the path length, and you add it up, right? So this is path along the line of sight. Okay. So if you recall our previous discussions of surface brightness and so on, there were similar things. Okay. So if you have a star of temperature less than 50,000 Kelvin, that's about 50,000 Kelvin is about the limit of the highest temperature of a star. Then the average energy of photons of Lyman continuum photons, basically the photons with greater than 13.6 eV, is about 18 eV, right? So not everything comes just at 13.6. It's like an exponential drop off, and so this is like rough energy for this is the average energy of Lyman continuum photons for like a 50,000 Kelvin star. So what is this average energy? This is nothing but nu naught to infinity L nu d nu divided by nu naught to infinity. Nu naught is this frequency corresponding to Lyman continuum, which is 912 angstrom. I actually do not. It's I do not know the value in hertz. It has to be some 10 to the 15 hertz. Okay, so this is h nu L nu by h nu d nu, and this is nothing but L nu by h nu d nu. This is the definition of average energy of the Lyman continuum photons from this star. Okay, so this is like typical value. The sigma pi. The sigma pi is the photoionization cross section. Okay, photoionization cross section is 0 below the ionization potential. Right? You cannot ionize if your photon has energy less than the ionization potential. So sigma pi is 0 at frequencies less than the ionization potential, or energy is less than the ionization potential at about 18 eV, which is the typical energy of Lyman continuum photons from this 50,000 Kelvin star. This is about 3 times 10 to the minus 18 per centimeter square. No, centimeter square, not per centimeter. Okay. Right. So it's actually a good idea to have some sense of sigmas in mind. The Thomson scattering cross section is 6 times 10 to the minus 25. Thomson scattering cross section is the interaction of uh, you know electromagnetic wave with an electron, and the cross section for that is 10 to the minus 20, 24, roughly 10 to the minus 24 centimeter square. So this is like orders of magnitude higher cross section, right? Uh, Similarly, people talk about dark matter interaction cross section. That's like 10 to the minus 43 or something. It's an extremely weakly interacting uh, uh, particle, dark matter. Neutrinos have extremely small interaction cross sections. It's useful to have these things, order of magnitudes in your head. Okay, sigma pi. It's this. So the question is, how far does a photoionizing photon go in this? So there is this fully ionized region, and then there is a fully neutral region. So an ionizing photon at the edge, how far does it go into the neutral medium before, basically the mean free path of a Lyman. So what we are is after is lambda mean free path of the Lyman continuum photon. That's nothing but 1 by n hydrogen times sigma pi, right? So you have a photon, there is neutral hydrogen. How far does it travel before getting getting absorbed? Right? So this is that path. Mean free path is 1 by n sigma. So if you plug in the numbers, what do you get? So this 3 times 10 to the minus 18 for sigma, and for number density, we had assumed 100 particles per cc. So this gives you about 0.1 parsec nh to the minus 1. Yeah, this is what you get. So higher the density, sharper is the edge. So this is basically the, so you have this, let's see, how do we do? So let's actually schematically plot x versus r by r s naught. R s naught is the size of the radius of the Stromgren sphere. So at about 1, so x is the ionization fraction. So ionization fractions. So x equal to 1 inside this. Right? So basically, this is 1. It's fully ionized. Outside, oh, wow, it's fancy. This is how it looks like. The simple model is a step function. Everything is fully ionized. Outside, everything is neutral. But there is this like a length scale associated with this. What is that length scale? That length scale is this. This is the mean free path of the Lyman continuum photon. It's like, what is the size of the shock? What is the, if you have a shock, if you've done hydrodynamics course, the scale over which the shock transition in the gas happens is about the mean free path, the collisional mean free path. Here, this is photoionization mean free path. Okay, and you actually see that this is much less than RS naught, right? Which was about 3 parsec. You remember, if you plug in the typical numbers, we got an RSO which was 3. So 0.1 is indeed much less than 3. So this transition is actually indeed quite sharp. So we made those 4 assumptions, and this argument tells us that yes, you can make this assumption that everything is ionized inside, everything is neutral outside, because the transition happens on this length scale. Okay, so the assumption of sharp transition is justified for most conditions. Okay, so what about the tau? So there are time scales. Okay, so we'll list time scales. So it's useful to be aware of certain time scales. So what are the different time scales? So tau ionization. What is tau ionization? So this is the time scale required to establish a Stromgren sphere. So at t equal to 0, everything is neutral. You put a O star and ask on what time scale will you establish a steady Stromgren sphere. Okay, so that's what. So this is equal. So this is equal to uh, number of hydrogen atoms to ionize divided by number of Lyman continuum photons per unit time, right? So the number of hydrogen atoms that we need to ionize is NH times the volume of the Stromgren sphere. Right? That's the total number of hydrogen atoms to ionize. And every photon, every Lyman continuum photon ionizes one neutral hydrogen. So this is the time scale over which you will be able to ionize the required number of hydrogen atoms, right? So that's nothing but 4 by 3 pi r s naught cube times nh divided by q naught. But we can write rs naught in terms of q naught. In fact, this is what, so nh squared, if you try, right. So the definition of your Stromgren radius was that 4 pi by 3 rs naught cube nh squared times alpha was equal to q naught. Right? The total number of ionizations is equal to total number of recombinations per unit time. So what this will give you, this is equal to 1 by alpha b, this recombination coefficient times nh, right? This is what you'll get, because if you do nh times nh times alpha, you divide by alpha and nh. So this is what your time scale is. This is the ionization time, and how much. So this is, these do not depend on q naught and all that. This is just 1.2 times 10 to the 3 years divided by n2. About 1,000 years, right? If you turn on an O star now, in 1,000 years, it will establish a Stromgren sphere, which is 1,000 years is a short time compared to like mega year time scales of the lifetime of O star. So second, another assumption that the lifetime of O star is long compared to the lifetime of Stromgren sphere is also justified here. Okay. This, by the way, the recombination time, tau recombination, is equal to NH, number density per unit volume, divided by recombination rate per unit volume, which is alpha b Ne Np. Right. So this is number of recombinations per unit volume per unit time. This is number of hydrogen atoms per unit volume. So this is a time scale, and this is nothing but the above number. Right? In steady state, ionization and recombination are balancing. That's why these two numbers have to be equal. The rates of creating the reactants has to be equal to the rates of creating the rates of destroying the product of the reactants should be same as the rate of creating the product. So the forward and backward reactions are balancing in this case. So that's why these two time scales are the same. Okay. So what does it mean? If you have a Stromgren sphere and if you suddenly switch off your central star, right, the electrons and protons will start recombining, and that happens on this time scale, the same time scale, thousand year time scale. What about the time scale of this overpressured thing, overpressured bubble that you have created? On what time scale will it expand? Let's see, how much hydrodynamics do you know? You have created this overpressure bubble because ambient medium is at 100 Kelvin. This is at 10 to the 4 Kelvin, and it has a density higher, double that of the ambient medium. So it has a pressure 200 times higher than the ambient medium. So on what time scale will it start expanding? Higher pressure region will expand, but on what time scale does that happen? The expansion. Any guesses? What is causing the expansion? The pressure excess. And the pressure information is propagated on the sound speed. So basically, the expansion time will be RSO, the size of the region divided by the sound speed in the Stromgren sphere. Right? So this is and if you plug in the typical numbers, this is 3 parsec, and the sound speed of a 10 to the 4 Kelvin. So this ionized region will be 10 to the 4 Kelvin. This temperature is determined by the thermodynamics, like heating and cooling processes within this H2 region. But 10 to the power 4 is roughly the ballpark number for photoionized plasma. Okay, so this is what is the sound speed in a 10 to the 4 Kelvin gas? It's about 10 kilometer per second. So this is about 1 parsec per kilometer per second is 1 mega year. Very useful. Parsec plus per kilometer per second is a mega year. So this is 0.3 mega year, which is of course much longer than this time scale, right? So that's great that you can ionize much faster than this ionized bubble expands. So this assumption that on the expansion time scale, the density structure will change, right? You have higher pressure thing, it will push your medium out, and it will reduce the density further inside it will reduce the density inside the bubble, and it will push the ambient medium. But that all happens on a much longer time scale. So even the other assumption that you can assume the density to be constant as the initial value is justified. So case B. The fourth assumption was this case B, reionization. Case B was that you ignore all the recombinations to the n equal to 1 state because transitions to n equal to 1 state produce photons which are almost immediately absorbed by the ambient neutral hydrogen. So it's as if those recombinations never happened because they're immediately undone by uh, the reverse process. So let's see. So you have this proton, and you have these different energy levels in hydrogen atom. Right. So recombination can happen here, here, here. There is a probability for recombining in any of the states. But once it recombines here, there is a cascade of these transitions. You can go from here to here, here to here, and here to here. Okay. And I actually already mentioned this point that the Einstein A values are very high. So these highly excited states are almost immediately all decaying to lower transitions. So this photon, say this is n equal to 2. This photon has an energy. So this photon will have an energy which is this is say Balmer line. So Balmer continuum starts at, let's see. So Balmer continuum is n equal to infinity to n equal to 2. So it's like 1/4 of the ionization potential, right? This is the energy of the So all these transitions which happen to n equal to 2 or higher have produced energy of photons which are 1/4 time the ionization potential. So all these photons which are produced due to these transitions will just escape the system because every neutral hydrogen is in the ground state. And if you have photons which have 1/4 or lower energy than the ionization potential, they are essentially not capable of photoionizing. They just escape. So that's why H2 region will emit a lot of H alpha, H beta, and even higher transitions, but no Lyman alpha, beta, and so on. The other thing is the sigma for uh, say n equal to 2 to 1 and n to 1 transitions. These are line transitions. It's uh, about 10 to the 5, 10 to the 4, 10 to the 5 times sigma of photoionization. So basically, these line transitions, I mean, if Lyman continuum is optically thick, these line transitions are extremely optically thick. N equal to infinity to n equal to 1, uh, or n equal to 1 to infinity transitions are optically thick, but n equal to 1 to 2 or 2 to 1, and all these are even more optically thick. So in these regions, uh, the photon will do a random walk. If you have a Lyman continuum photon, it will just be all trapped, and just it can escape, but in that damped wing, if there are velocity differences, then it can actually go in the damped part of the line profile. It can escape. But anyway, so that's why case B is a justified thing here. Okay. So what about uh, neutral fraction in uh, an H2 region? So I already said that close to the center, H2 region is almost fully ionized. Beyond the edge, it's fully neutral. But is there a structure? Can we actually determine it? We can. This equilibrium between ionization and recombination happens not just in the global sense, but also locally, because nothing is changing in time. So at every radius, the number of ionization happening per unit time is equal to the number of recombinations happening per unit time, because the net ionization state is not changing in steady state. So what is it? So let's define something called Q as a function of R. This is equal to Q naught minus 0 to R NH squared alpha B uh, x squared 4 pi R prime squared dr prime. Okay, what is this? This is this is the number of Lyman continuum photons produced by the star per unit time. This is uh, total number of recombinations within radius r. But this x is the ionization fraction. So uh, x times nh is equal to ne. And this is also equal to np, because it's a hydrogenic plasma. Number of electrons and number of protons is the same. So ne times np times alpha b is the number of recombinations per unit volume per unit time. This times the volume within radius r is the number of recombinations happening within that radius, right? So QR is the number of Lyman continuum photons crossing radius r, right? So this is the number of Lyman continuum photons crossing a radius r. So if you go to r greater than rs0, this is 0, because there's nothing. There are no Lyman continuum photons beyond the Stromgren sphere. Okay, so this is the first thing. So this we can actually write as Q naught times 1 minus 3 integral 0 to R by RS naught. So now what I'm doing is I'm just de-dimensionalizing this integral. So this x squared is the ionization fraction squared, y squared dy, where I have done this change of variable to y, which is equal to R prime by RS naught. And I have used the definition of, I have used the relation between NH Q naught and RS naught, right? So we know that 4 by 3 pi RS naught cube times alpha b times nh squared is equal to q naught. This is what we have used to express things in this way, in the dimensionless form. And we know that q0 is equal to q0. I mean, basically, there are no recombination just outside the star. And q rs is equal to 0. Okay, so this is again sort of a, this is applied at every radius. So let's see. So balancing photoionization and recombination at a radius r, what do we get? So we have nh squared alpha b times x squared. This is ne times np times alpha b. So this is the number of recombination per unit volume per unit time is equal to qr by 4 pi r squared, right? So this becomes number of ionizing photons per unit area per unit time. So this becomes a number flux times nh times 1 minus x, right? This is the, so nh times 1 minus x is the neutral hydrogen density. This nh is the ambient hydrogen density. nh times 1 minus x is the neutral hydrogen density at a radius r times sigma pi right. So this is also n sigma. So this is also a number per unit. So this is number per unit area per unit time, right? So this is also a rate per unit volume. So we have actually equated the recombination rate per unit volume at a given radius and the ionization, photoionization rate per unit volume at that radius. In steady state, they have to balance. Okay. So what can we do? We can like rearrange this equation and write it in this form. So x squared by 1 minus x. So we bring x together. X is unknown. X is what we are after, right? The ionization fraction is equal to q r by q naught times nh sigma pi photoionization cross section r s naught by 3y squared. Recall, y is just this. Y is the y is the d-dimensionalized radius, right? This 1 by r squared gives you that 1 by y squared. And we have just plugged in things in terms of rs0, right? This alpha b and so on, we have plugged in terms of these quantities. Now this number is nothing but the photoionization. So n sigma, so 1 by mean free path rs naught. So this is nothing but rs naught by lambda mean free path of the photoionizing electron. Right, so that's just optical depth. This is tau s naught. Right, what is optical depth? Optical depth is just the ratio of the length and the mean free path. So if mean free path is small compared to the size of the system, then optical depth is high. If it is small, then it's optically thin. Okay. Now this also we can plug in terms of q naught and everything. Right? So tau s naught, the optical depth of the photoionization optical depth of a Stromgren sphere is about 3,400 q naught 49 to the 1/3 times n2 to the 1/3. I mean, rs naught was proportional to q naught to the 1/3 and n2 to the minus 2/3, but you're multiplying it again by n. So it gives you this. Now, the point to notice is that this is much bigger than 1. The optical depth of a Stromgren sphere is much bigger than 1. So your equation becomes x squared by 1 minus x is equal to, this is equal to qr by q naught times tau s naught by 3y squared. Okay, so let's see. When qr is about q naught, which is towards the center of the Stromgren sphere, close to the star, this is 1. This is very big, right? Tau s naught is like 3,400. Y. So if this is big, basically what it, and x cannot be greater than 1. X is less than 1. It's ionization fraction. So what it means is that near the center, x is 1 minus x tends to 0, right? So when you have x squared by 1 minus x, it gives you a big number, right? And y is also right. So 1 minus x tends to 0 as y tends to 0. And similarly, what you can show is that, let me see. Now, so if you solve this system of equation, what you'll find is in most of the Stromgren sphere, because of this large tau naught, tau s naught, in most radii r less than rs naught, x is actually close to 1, right? Because this is a very big number at all radii. So if you plug in x equal to 1 in the first equation, in this equation, if you plug in x equal to 1 in this equation, as I said, with most radii, x is about 1. So if you plug in 1 here, what we get is qr by q naught roughly equals 1 minus y cube, right? So if x is 1, this just gives you y cube by 3, and that just gives you this. And if we come back to this equation now and substitute this qr by q naught, we get x squared by 1 minus x is equal to, so qr by q naught is 1 minus y cube tau s naught by 3y squared. And remember, tau s naught is big. It's like 3,000. So let's see. So when y goes to 1, right, y goes to 1, meaning r going to RSO. This right-hand side goes to 0. So that means as y tends to 1, x tends to 0. So that's what you expect. And all these are heuristic arguments. You can actually do the math. What you can do is you can solve these two differential equations. So this and this. If you solve together, you can solve for x as a function of r. Okay. So this is about the Stromgren sphere. So I think we'll end the class here.